All right, now we're going to start chapter 6, which is the last chapter before your next unit test. And your unit test is going to be on chapters 4, 5, and 6. Chapter 6 is an important chapter because this is where we learn how to speak chemistry. When you talk about chemical compounds, there's ways of naming them, and that's called nomenclature. And this is something we'll use now for the rest of the semester, and any other chemistry class you take, you're going to do inorganic nomenclature. In other words, how to name compounds. Okay, when we talk about nomenclature, we're talking about a system for naming chemical compounds. And there's a lot of common names, like we call sodium chloride, we call it salt. But there's all kinds of other salts, and salt doesn't tell you what's in it. So we have a system that tells you what substances you have. Okay, so we're going to use that system. Yeah, we use common names as well, but they're not based on anything. They're kind of just based on something that happened, some sort of history that happened to them, but there's no real rules to those. Okay, so that's N2O is nitrous oxide. If you've ever gone to the dentist, had a laughing gas. But its real name, its systemic name is dinitrogen, there's 2 nitrogen, monoxide, 1 oxygen. So we're going to go through the systemic system, the way that tells you what's in the compound. Okay, we're not going to worry about the common names. Okay, again, here's water. Okay, we all know water is H2O, but why do we know that? Okay, if we really named it dihydrogen monoxide, or it's actually really hydrogen hydroxide. And here's ammonia. Ammonia is NH3. Well, that doesn't really, it's kind of weird because it really doesn't tell you what's in it. So there are some common names that we use for substances that we use a lot. Okay, the common names don't tell you really what the physical or chemical properties. It doesn't tell you what's in it. You have to already know kind of ahead of time. All right, common names are often used because systemic names sometimes can be too long. Like CaO, that's calcium oxide. It tells me there's calcium and oxygen. Its common name is lime. Okay, but not everybody else, and I don't mean the green stuff. I mean like the white powdery stuff that you find in the soil. But a lot of people don't know that. Okay, so that's the other thing about common names. Some people know them, some people don't. All right, so as a chemist, we prefer to use systemic names because it tells you what you have. It tells you what elements, and it tells you the composition of those elements. Okay, so there is a system. It's the IUPAP, which is the International Unit of Pure Applied Chemistry, has rules. We're going to go through these and learn how to name chemical compounds so we can speak chemistry, if you want to call it that. Okay, all right. The formula for most elements is, we've seen those on the periodic table, like sodium is Na. And again, sodium is one of those old ones. So it doesn't make sense for its name, but it really does because its old name is nerium. Okay. And then we have the polyatomic ions. We've talked about these before. There's some of them that when they're by themselves, there's 7 elements that will not exist as a single element. Okay. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. When they're pure, okay, they're not combined with anything, but when they're pure, there's always 2 of them. They're diatomic, okay? That doesn't mean if they combine with something, there has to be 2 of them. It just means when they're in their pure form, there's only these 7 elements. All the rest of them, that's not the case. There's just one. Like sodium is Na, copper is Cu, calcium is Ca. That works that way, okay? And there's a couple other weird ones, like sulfur can exist with 8 of them and phosphorus with 4. We're not going to talk about those too much. We're going to stick with the standards, okay? All right. We also talked about a charged particle. When electrons move around, we get an ion. And an ion is either add electrons or take away electrons from the neutral atom. Because again, remember, we're talking about atom, the protons and the electrons equal each other. But electrons can move around. And so if you lose electrons, remember we said it becomes a cation? It's an ion now, it's a charged particle. Well, the thing with chemistry, we always talk about positives and negatives are attracted to each other. So a cation is going to be attracted to an anion, and that's how they make a compound. Okay? Potassium has 19 protons and 19 electrons. But potassium only has 1 in its very outer energy level. Okay, it only has that. It needs either to pick up 1, or it needs to pick up 7 or get rid of 1. So it's just going to get rid of 1. It's just easier there. So it'll give up its 1. And now because it has lost one of its electrons, now it becomes positive 1. So it becomes a cation because it has 19 protons. That doesn't change, but the electrons changes to 18. So now if you look at the charges, you have an extra positive. So potassium becomes an ion. And in your page, I'll have a chart. It's called periodic table of ions. I would suggest you run that off because it's really handy for naming compounds. Okay, so again, we talked about this before. If potassium loses an electron, it becomes positive, and then it's a cation. Okay, remember we're positive, the cat's in trouble. That's why we know the positive one's the cation. Okay, a neutral atom loses an electron, it becomes a cation. All the metals will do that, you guys. Okay, the metals are very, very giving. They're more than willing to give up their electrons to a non-metal. Okay, so anytime you put a metal and a non-metal together, the metal is going to give up its electrons and the non-metal is going to take them right in. Okay, so again, we have potassium as an ion, we have potassium as an atom. If they, the cations, you know, all you have, the only difference between it is you have that charge. If, like here, magnesium gains 2 electrons, gives up 2 electrons, it's +2. Aluminum actually gives up 3 electrons and it's +3. So the plus is how many they give up. Okay, and I talked about that, magnesium and aluminum. Okay, so how many electrons they give up? The first column in the periodic table, potassium, sodium, all those guys down, they all give up 1. So they're all a +1 charge. The second column, beryllium, magnesium, calcium, they all give up 2, so they're +2. And then aluminum, there's not a whole lot of elements that give up 3, but aluminum's one of them. Okay. Then we have the other ones, the chlorine, or what we'd call the nonmetals. Chlorine is one of the halogens. In order to be stable, chlorine has 7 on the very outside. It's looking for 1 more. 8 is the magical number. So it has 17 protons, 70 electrons. It picks up 1 electron, usually from a metal. And now because you have an extra negative charge, it becomes an anion. It becomes a negatively charged particle. Okay? And again, oxygen has to pick up 2 electrons. Oxygen has 6 on the outside. It's looking for 2 more. So you can see 2 negative or -2, whichever way you want to write it. This means oxygen actually, as an ion, picks up 2 electrons. And if it was 3, like phosphorus and nitrogen, that would be, you know, a -3 sign. Okay? And here are some comments. Now, when you name ionic compounds, when you name a compound with a metal and a nonmetal, you change the ending of the second one, the negative one, to IDE. So instead of fluorine, it'd be fluoride. On that chart that I have in there, it already did that. Okay, it already has the names changed for you. Okay, so chlorine is chloride and so on. Oxygen is oxide. Hydrogen is goofy. Hydrogen can be the first or the second. It can be positive or negative. Again, hydrogen is a rebel. So hydrogen would be hydride. Okay, now we're also going to talk about, later on we're going to talk about molecular compounds. Then you leave these names. You only change the ending if it's the second one listed, the negative one. Don't do it if it's the first one. And again, you'll see later what I'm talking about there. But on that chart I gave you, on the negative ones, the anions, it already did change the ending to IDE. So it made, instead of listing it as fluorine, it's listed as fluoride. It's a special periodic table. Okay. What am I doing time-wise? Okay. All right, so ionic compounds have a cation and anion. You take a positive and a negative and you put it together. How do I know it's an ionic compound? If it's a metal and a nonmetal. Okay. If you have 2 nonmetals, that's not going to be an ionic compound. If you have 2 metals, that is not going to be an ionic compound. It has to be a metal and a nonmetal. Okay. Overall, they have to have a charge of 0. So if the anion is a -1, the cation has to be +1. They have to equal each other. Okay. Here's some. Okay, so I'm going to write the formulas, and I'm sorry my face is in here, but here I have sodium and bromine. So when I'm going to write the formula for sodium bromide, I'm going to write the symbols and I'm going to write the charges. And these charges, again, are on that table I was telling you about. Notice how they equal each other? +1, -1, you don't have to do anything. The formula is NaBr. You get this right here, you guys, don't worry about it. I'll show you a simpler way of doing this. This is for people that have way much too much time on their hands. Okay, here I have potassium with a +1. I have sulfur with a -2. They do not equal each other, and I need them to equal each other. So what you do is you crisscross. You bring the 2 down here. Okay, you don't have to write a 1, but bring the 2 down here. Now it becomes K2S, potassium sulfide. Okay, here's zinc, which is a +2. Now this is sulfate, and again, if you can't see it through my face, I'm sorry. Sulfate is a polyatomic ion. A polyatomic ion is a molecule with a charge. And on that chart that I gave you, it has the polyatomic ions listed in the middle. So these guys stick together like a molecule, but overall they have to have a charge. Okay, so these guys are both the same. +2, -2. Don't have to worry about it. If the charge is the same, you don't have to do anything. Just write the symbols. Okay, here I have ammonium. NH4 is ammonium. It's a polyatomic ion and has a +1 charge. Okay, here I have phosphate, PO4, and it has a -3 charge. It's not the charge down here, you guys. It's the number up here. Okay, so this one is 1 and this one's 3. They don't equal each other, so I need to put this 3 down here. But because this is a polyatomic ion, I need this whole group. Okay, if I just write a 3 here, it looks like NH43. I want this whole group, so I'm going to put it in parentheses and put a 3. So anytime you have a polyatomic ion and you need more than 1, put in parentheses. Okay, so you can see how I did it over here. I didn't do it, the book did, sorry. But NH4 in parentheses 3, PO4. This is the compound formula for ammonium phosphate. You don't just write the symbols, you have to make sure the charge is balanced. Okay, here's aluminum chromate. Again, aluminum is +3. Chromate is CO4. It's one of those polyatomic ions and it has a -2. So I'm going to put the 2 over here and I'm going to put the 3 over here. And again, I have to put this in parentheses. Now, if you look, 2 times +3 is +6. 3 times -2 is -6. So they equal each other, +6 and -6. Instead of doing this least common multiple and all this crazy stuff over here, just crisscross them. If they equal each other, you don't have to do anything. If they don't, you crisscross them. You put a 2 here. Here they equal each other. You didn't have to do anything. Here I had to put a 3 down here, and so on. So that's how you write the formulas for ionic compounds. Okay, so again, write the metal ion formula. If it's Ca, it's calcium. If it's Cu, it's just whatever its name is, write its name that way, okay? And then the second one, the non-metal, you change the ending to IDE. Now, if you're writing the formulas, write the symbols, okay? And then crisscross the charges. And again, here talks about smallest whole numbers and all that. You can do that, but honestly, you guys, all you have to do is write the symbols, put the charges above, and again, they're on that chart I give you. And then if they don't equal each other, use subscripts, crisscross them, okay? All right, here's the formula. Write the formula for barium nitride. Okay, barium's Ba and it's +2. Nitride is nitrogen and it's -3. Okay, so these I get right off that chart. They don't equal each other, so what I'm going to do is I'm going to put a 2 over there and I'm going to put a 3 over there. So the formula is going to be Ba3 and 2. Don't write this charge down here. Okay, it's got to go opposite. Okay, so there's your correct formula. And again, I probably should take this stuff out. You don't have to worry about this common multiple and all that. Just crisscross them. It works out and it's a lot easier. I'm of the school, keep it simple. KISS, keep it simple, stupid. That works for me. And I'm stupid. That works for me just fine. So just crisscross, okay? All right. Chemical formula for magnesium oxide. Magnesium is Mg. It's +2. Oxygen, O, -2. They equal each other, so it's just got to be MgO. Okay? If they're both 2, you don't have to write 2 and 2. If they equal each other, they cancel each other out. Okay? And that goes through all that stuff again. Okay? So when we're talking about elements, we're talking about, right now we're going to just do binary where they're made out of 2. We're going to run out of time here, so we're going to do this naming stuff slowly. So I'm going to have you work on naming these compounds, a metal and a non-metal. Make sure you run off that periodic table. You'll really need that. That'll help you, and you can use it though, you'll need it for the whole rest of the semester. So make sure you run it off. So we'll quit now, and then we'll hit this next time.